Welcome to this lecture on modeling analysis and estimation of three-phase unbalanced power network. From this lecture, we will start today a new topic on three-phase static state estimation. However, in this lecture, we will not derive the basic equations of the static state estimation in great detail, because these details have already been covered in adequate detail in our previous course on computer aided power system analysis. But here we will first definitely recapitulate the basic method as well as the basic equations, and after we review the basic methods along with the basic equations, we will then see that how to apply this method for the static state estimation of a three-phase unbalanced power network. So, we will first start with the recapitulation of the static state estimation method. So, we write that review of static state estimation method. So, essentially we shall be talking about the most common weighted least square technique. So, we essentially talking about WLS technique. So, essentially what happens is that I have a power system, n bus power system for example. To start with, let us assume, because we are now trying to essentially kind of review. So, let us first assume that we are talking about a balanced system. So, then for a balanced system, my unknown states to be estimated. So, states to be estimated are theta 2, theta 3 to theta n and V 1, V 2 to V n, right. Theta, so where theta I is the voltage angle of the ith bus, V I is voltage magnitude of ith bus. Here of course I varies from 2 to n, here of course I varies from 1 to n. The reason is that we take theta 1 to be 0, which is nothing but the reference angle. So, we put them in a vector x, and that x is say theta 2, theta 3 dot 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 theta n, and then V 1, V 2 dot 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 V n transpose t. So, of course, this is a 2 n minus 1 cross 1 vector. Now, to estimate this, we take a certain measurements. So, we take measurements Z, we put measurement Zi, where I is 1 to m, m is the number of measurement. Right. Usually, to take into account the aspect of the bad data detection as well as a bad data removal, always we make m is greater than equal to n, always m is greater than equal to n. So, then therefore, we put this measurement vector z. So, measurement vector z as z1, z2 to zm. Here I have made a mistake. This m must be greater than n. This is a mistake. So, here m would be greater than n is equal to 2n minus 1, where n is this is the number of states to be estimated. Right. So, well, so now, so then we have now got z. So, zm is equal to, so it is an m cross 1 vector. Now, what happens is, now I mean these z's, I mean these measurements can be, for example, pi, that is injected power at ith bus, injected real power qi, it could be real power flow over the line pij, reactive power flow over the line qij, magnitude of the current flowing over the line ijvi, that is basically the magnitude of the voltage at ith bus, etc., etc., etc. Now, for example, suppose for example that I do have one measurement P2, suppose I do have one measurement value is P2, say for example Z2 is equal to P2. So, then obviously that P2 is given by J is equal to 1 to n V2 Vj Y2j cosine theta I minus theta j minus alpha 2j. So, here you see, sorry, it should be theta 2. So, theta 2 minus theta j minus alpha 2j, j is equal to 1 to n. So, then obviously I can write down that it is some function P2, we also call this function P2, and this is the function of the unknown states theta 2 to theta n and V1 to Vn. So, I can say that this is a function of the state vector of x. So, then therefore, I can ultimately say that Z2 is equal to P2, which is the measured quantity, but this quantity is a function of x, this unknown vector x. So, we say that in general it is H2x, right. So, here H2 is the measurement function, I can say that this is second measurement function, right. So, in this particular case, because we have said that my second measurement is nothing but the injected real power measurement at bus I. So, then therefore, this H 2 is equal to P 2, correct. So, then similarly for every measurement I can say that Z I would be some corresponding measurement function H I, which would be, and all of them would be the function of x, right. So, here we say that H I is the ith measurement function. Measurement function. So, then now what I have? So, I have got this measurement is Z I is equal to H I x, but this measurement model, I mean this is the ideal case, this is the ideal case, but what we have is that every measurement has got their error. So, my measurement model is actually Z I is equal to H I x plus E I. E I is the error. What is E I? E I is the error, random error of ith measurement. And we say that, take an assumption about the statistical property of these errors. We say that this errors has got their actually every error E I is basically 0 mean standard deviation or rather variance square sigma I square, right. So, I mean 0 mean and my variance is sigma I square. So, this is the Gaussian distribution. So, we say that every measurement error is essentially a random quantity and the underlying probability density function is essentially a Gaussian distribution Gaussian function which has got 0 mean and with a standard deviation of sigma I. So, it is a Gaussian PDF, correct. So, then therefore, as a vector I have got Z is equal to h of x plus E, vector E. This vector Z we have already defined. What is this vector h of x? This vector is the h of x is, we write that h of x is h. So, this is the vector of measurement functions. So, essentially, so then therefore, h of x, please note this x bar inside the bracket denotes that this vector is a function of the states to be estimated. So, these are basically h 1 of x bar, h 2 of x bar dot 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 h m of x bar transpose t. And what is this vector E? Vector E is the vector of, so it is also m cross 1. Vector of random measurement errors. measure errors, and this E is given by E1, E2 to EM transpose. So, what I have, that I have got this model. So, I mean, this is the state estimation model. So, essentially we call this state estimation model. So, this is the underlying equation, right. So, this is the underlying equation. So, now we have to estimate x hat from this set of equations. Now, please note that because m is greater than n, that is 2n minus 1. So, then therefore, this is an over determined set of equation, correct. So, it is basically an over determined set of equations. So, then therefore, we really cannot use any kind of, let us say, Newton-Raphson technique and etc., because this is an over determined set of equations, and also we have to also estimate this particular values of x hat such that the effect of E is essentially minimized. So, then therefore, to do this, so to estimate, what we do is that we estimate x by, so what we do is that in weighted least square estimation, we estimate x by minimizing some objective function j, which is given by z minus hx transpose, then w, and then z minus h x. Now, let us see. So, this is a vector z minus h x. So, it is a vector 1 cross m. This is an weight matrix, this is m cross m. I mean, what this weight matrix is, I mean, let us, and we will do it right now. And this is z minus x is m cross m. So, then therefore, this z j is a scalar quantity, it is in 1 cross m. And what this weight matrix is? It is basically a diagonal matrix. It is weight matrix is basically a diagonal matrix which we call R inverse. It is diagonal 1 by sigma 1 square, 1 by sigma 2 square dot 1 by sigma m square, correct. So, to minimize it, what we do is that we do that z del z by del x hat. So, del x 0. So, that gives me a relation that h of x transpose w z minus h x is equal to 0. What is h x t? H x t is the Jacobian matrix. H x is the Jacobian matrix, which is nothing but we can write down at del z by del x. Now, because these functions h x, these are all nonlinear functions. So, then therefore, there is no direct solution for this. So, then therefore, you have to do an iterative solution. So, we start with an initial So, iterative solution is only possible. So, iterative solution is only possible because is only possible, right. And then what do we do? That we start with an initial guess x naught, we start with an initial guess x naught, which is uh, initial guess, and then with this at k plus 1th iteration, we update it as x k plus delta x k, where delta x k is given by g, what do I write, x inverse h x t w z minus h x, where g x is given by h x t w h x. So, this is called the gain matrix. And x k is nothing but the estimated value of estimated vector x at kth iteration. So, we start with this. So, then therefore, we start with an x naught, and I should write that. So, I mean how, so then what do we start? So, we basically start with an x naught. With this x naught, we do calculate h x t, w and h x at x is equal to x naught. So, now what is g x here? Now, what is h x? H x is, it is the, I mean, Jacobian matrix. So, del z by del x. So, it is basically del z 1 by del x 1, del z 1 by del x 2 dot 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 del z 1 by del x n, and so on and so forth, del z m by del x 1, and then dot 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 del z m by del x 2, and then dot 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 del z m by del x n. So, this is h x. So, what we do at every iteration, we start with, for example, we start with x naught. With this x naught, we first calculate h x, I mean we first compute, or rather we first find out the analytical expressions of all these terms, and then we evaluate this particular matrix H s at x is equal to x naught. Then we calculate g x. Once we calculate g x, and then we then calculate delta x k is equal to z minus h x k, right. So, here I should write it down that it is, I should write it down x k. So, this h is being evaluated at x k, and I also should write it down in a little better way, little better way, I should write it all this down in a little better way to make it more. So, g x k inverse and h x k transpose. Let me write it down in a more looking very dirty. We should let us write it down in a more. So, it is G x at kth iteration and I take inverse of it, then Jacobian matrix at kth iteration, the transpose of it, and then this W matrix, and then Z. These values are already given, H x k this. So, this is the complete expression. This of course not there. And what is G x k? G x k, so this is G x k, so this is k. So, I must write it down also in a more clearer way. So, let me write it down in a more clearer way. H x k transpose W H x k. And what is H x k? So, this is it, and it is evaluated at x is equal to x k, right. So, this is evaluated at x is equal to x k. So, that is H x k. So, essentially that is how we proceed. We start with x naught. So, for example, here we start with x naught, k is equal to 0, we start with x naught. With this x naught, we first evaluate h x 0. Once we get this h x 0, then after that we calculate g x 0. Once we get this matrix g x 0, then we calculate delta x 0. Then we calculate x 1 because k is equal to 0. So, then we calculate x 1 is equal to x naught plus delta x 0, right. So, we get the value of x 1. Then we update k is equal to 2. Then we, so then after that in the next iteration we calculate h x 1. So, this matrix is evaluated at x is equal to x 1. Then we calculate g x 1. From this we calculate delta x 1. Then we calculate x 2 is equal to x 1, which we have already calculated in the last iteration, plus delta x 1, and we keep on doing it till the magnitude of this vector delta x k becomes less than some epsilon till convergence. Of course, these derivations we have already done in a much more great detail in our earlier course on computer aided power system analysis. So, we are not really again really I mean deriving it, but then that is how we do it. So, then therefore, what is the essential point? That essential point is that we have got measurement vector z, and those measurement vector z are expressible in terms of some measurement function vector h of x bar. X bar is the nothing but the states to be estimated and which are corrupted with E. So, with this underlying equation, and because this m is greater than n, so then therefore, it is not possible to solve for x uniquely, and also simultaneously you have to estimate the values of x such that the effect of errors are is actually getting minimized. So, then therefore, we do some optimization. Why it is called weighted least square? Because we are using an weight matrix W. So, this is the case. So, now, so then therefore, so I mean this is the basic method of the weighted least square technique. Now, we will see from the next lecture onwards that how to apply this method for the case of static state estimation of a 3-phase unbalanced network. Thank you so much.